is a transmission line? Well, this is a transmission line. This is a transmission line. This is a transmission line. These are transmission lines. This is a transmission line. 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 Transmission lines take on many shapes and sizes. Basically, a transmission line performs one function. It delivers energy from a source to a load. Now, the source might be a huge power plant, generating millions of watts of power, enough to light an entire city a few miles away. Or a transmission line might be used to deliver a few millionths of a watt of energy to a sensitive measuring instrument only a few feet away. In all cases, a transmission line delivers electrical energy from one point to another. In this film, we will cover the transmission of high-frequency energy, often called radio frequencies and video frequencies. That is, complex waveforms with many fast rising and falling pulses. Mainly, we are going to deal with the theory of transmission lines and their characteristics. There are two basic types of lines: the parallel line and the coaxial line. A parallel line simply consists of two or more wires parallel to each other, suspended in some dielectric medium. Here's an example of a parallel open wire line, using air as a dielectric material. The wires are held in place by insulating spacers. Here is another example of a very common type of parallel line. A coaxial line consists of two conductors concentric with each other. Here we have a center conductor surrounded by insulating material. A metal braid or shield over the insulation serves as a second conductor. The insulating material between the two conductors is the dielectric. Here is an example of a coaxial line using air as the major portion of the dielectric. The inner conductor is suspended at intervals by Teflon spacers. This type of line is used where very high power must be transmitted or where the losses must be kept to a minimum. There are many variations of these basic types of lines, each with different characteristics and power handling capabilities. Now, let's get into the real story of our film and discuss what happens in a transmission line. Imagine now that we have a simple open wire transmission line that extends to infinity. We also have a battery. Let's suppose that it would be possible for us to connect this line to the battery for a very short instant of time. Let's examine step by step what happens. At the instant the line is connected to the battery, the positive pole attracts electrons from the immediate area of the wire connected to it. The negative pole repels the electrons in the wire connected to it. As a result, current begins to flow, but before the current flow can extend any distance down the wires, we disconnect the battery. We now have an isolated charge or pulse of current flow in the line. We can represent this pulse of current by drawing a vertical pulse. Since electricity travels close to the speed of light, a pulse of current will travel down a perfect line at approximately 300 million meters per second. A microsecond is 1/millionth of a second. Therefore, the pulse will travel at the rate of 300 meters per microsecond, or 30 meters every tenth of a microsecond. After 1/10 of a microsecond, the pulse of current has traveled along the line a distance of 30 meters, or about 99 feet. At the end of 2/10 of a microsecond, it has traveled 60 meters, and so on. Since our line is infinitely long and has no losses of any kind, the pulse of current will continue at the same amplitude forever and never reach the end. We can send just one pulse or a series of pulses at whatever rate of repetition we desire. The pulses will simply follow each other down the line in the same manner we started them. According to Ohm's law, the amount of current that flows in a circuit depends on the voltage applied and the resistance present. What are the values of this pulse? Well, the voltage is equal to that of the battery. But what is the amplitude of the current in this pulse of energy? Assuming that this is a perfect line and has no DC resistance. Would the pulse of current be infinitely large as a result of no resistance? Well, of course not. There is a definite value of impedance present, which will limit the current flow. Let's explain this in more detail. A transmission line consists of two conductors in close proximity. Now, between these two conductors we have capacitance, distributed capacitance. Also, any piece of wire has some inductance. The effects of this inductance becomes noticeable at high frequencies. Therefore, a transmission line will act as if it consists of sections of capacitance and inductance. As a charge travels from one imaginary section to another, the distributed inductance must charge, then discharge into the capacitance. The capacitance must then discharge into the inductance, and so on down the line. Now, this establishes a definite relationship between voltage and current. In other words, there appears to be an impedance present which says that for a certain applied voltage, only a certain amount of current can flow in this line, just like Ohm's law. Now, this is known as the characteristic impedance of the line, or the surge impedance. The characteristic impedance may be stated as the square root of L over C, where L is the distributed inductance of the line and C is the distributed capacitance. The diameter of the wires will determine L, and the spacing between them will determine C. The length of the line, however, does not affect the characteristic impedance. If a line is doubled in length, both the distributed inductance and capacitance will increase accordingly. But as seen in the formula, the ratio between them will remain unchanged. Hence, the impedance will remain the same for any length of the line. Unlike a resistance, this impedance will not absorb power. It only establishes a relationship between the applied voltage and the current flowing in the line. Again, let's watch the action of a pulse traveling down a line. The pulse passes from one section to the next and on down the line. Again, the pulse passes from section A to section B to section C, and so on. After the pulse has passed on to a new section, the first sections have no further effect on it. Let's take section C as an example. Section C receives the pulse of energy from section B and passes it on to section D. Once section D has received the pulse, section C no longer cares what happens to the pulse. The purpose of each section of the line, then, is to pass the pulse on to the following section, and so on down the line, no matter how long that line might be. If the line goes on forever, the pulse will continue forever. That is, in our perfect line of infinite length. There is no such line, so let's assume that it ends after section C. We will connect a resistor at this point. Let's assume that the characteristic impedance of the line is 300 ohms. So we'll make the resistor a 300 ohm resistor. Now what will happen to the pulse? The pulse travels down the line from section A to B to C and is dissipated as heat by the 300 ohm resistor. As far as section C was concerned, that 300 ohm resistor looked just like more 300 ohm transmission line. So section C passed the pulse on. Of course, the resistor wasn't more transmission line. It was a load, and it absorbed and dissipated all of the energy. We have now terminated the line, and it no longer goes to infinity. Since the resistor is of the same value as the impedance of the line, the first part of the line doesn't know whether the rest of the line goes to infinity or not. Now the line is serving a useful purpose, delivering energy from a source to a load. Here is a pulse generator capable of producing a repetitive series of pulses, an oscilloscope for observation, and about 200 feet of 93-ohm coaxial transmission line. Our equipment is set up so the pulse generator will feed a continuous string of pulses into one end of the 200-foot line. We have connected the scope to display the signal as it is fed into the transmission line. We have terminated the far end by connecting a load resistor of 93 ohms, equal to the characteristic impedance of the line. Let's see what happens. The generator feeds a pulse into the line. We see the pulse displayed as it leaves the generator. The pulse now travels along 200 feet of transmission line and is absorbed in the 93 ohm resistor. In this case, the transmission line is serving its normal function of delivering energy from a source to a load. What if the load is not equal to the characteristic impedance of the line? Well, let's take a look at some extreme examples. Let's completely remove the termination, leaving the line open. Notice the scope display. Let's explain what we are seeing. The pulse leaving the generator is displayed at the start of the trace. The pulse travels along the line until it reaches the end. There is no load, no more transmission line, nothing. No place for this pulse of energy to go. Energy must be dissipated. There's no load to dissipate it. So the only thing the pulse can do is to turn around and travel back to the source. We see the returning pulse displayed on the scope a second time. This is called a reflection. The signal is reflected as if off a solid wall and sent back to the source. Notice again, if we connect the proper termination, the reflection completely disappears. Let's short-circuit the end of the line. Notice we have a similar effect. However, due to the direct connection between the two conductors at the end of the line, current is allowed to flow to the opposite conductor. The charges are transferred to opposite sides of the line as they are reflected. As a result, the reflected pulse is of opposite polarity, in this case, negative. According to theory, when we have a short or an open-ended line, all of the energy will be reflected. As you can see by the display, however, the reflected pulse is only 6/10 the amplitude of the transmitted pulse. Now, this demonstrates another fact. A transmission line has energy losses. Losses due to DC resistance, radiation, and dielectric losses. In traveling from the generator to the end of the line, the pulse loses energy and is no longer of the same amplitude. All of the energy arriving at the end of the line is reflected. As the pulse travels back to the generator, more losses occur, just as on the first trip. As a result, the amplitude of the reflected pulse is considerably reduced by traveling, in effect, a total distance of 400 feet. The oscilloscope shows us something else. A definite amount of time is required for electrical energy to travel along a transmission line. The very fact that there is a time difference between the initial pulse and the reflected pulse proves our point. As we read the information displayed on the calibrated scope, we find the time delay to be 0.51 microseconds. In other words, it takes exactly 0.51 microseconds for a pulse of electrical energy to travel through 400 feet of this transmission line, 200 feet down and 200 feet back. The pulse is not traveling at the speed of light, 300 million meters per second, as we might expect. If it were, only 0.4 of a microsecond would be required to travel 400 feet. An electrical pulse will travel 300 million meters per second, but only if the dielectric of the line is perfect. That is a vacuum, free space. In actual practice, we must use some other material for a dielectric rather than a vacuum. So, this introduces the term velocity factor. In an actual line, the energy will travel at some fraction of the speed it would travel in a vacuum. That fraction is the velocity factor. Typical examples might be 0.6 or 0.7, or in the case of some open wire lines, 0.95. The velocity factor of this line is about 0.785. So far, we have shown reflections under extreme conditions of mismatched terminations, that is, completely open or completely shorted. Let's go back for a moment to our proper 93 ohm load. We'll change that load to 56 ohms. Notice we have a reflection, but not as great in amplitude as an open or shorted line. Some of the energy is being absorbed by the 56 ohm resistor, but not all of it. Let's go to 22 ohms. Notice that the reflection is greater. We're approaching a short circuit condition. Back to 56 ohms. Now the proper 93 ohm termination. Now in the other direction to 150 ohms. Now to 330 ohms. Notice that we are beginning to approach open circuit conditions. Observe that only when the termination is the same value as the characteristic impedance of the line will all of the power be absorbed in the load. Only then will there be a maximum transfer of energy with no reflections. If we are dealing with sine wave radio frequency signals, any reflections due to a mismatched termination produce what are known as standing waves on the line. If we are dealing with pulses or video signals, any reflections due to a mismatched line can cause serious distortion of the signals under observation. Here is an example. We'll take the same line as before and apply a square wave or any complicated waveform. The line is properly terminated. Now, let's remove the load. Notice the serious distortion. Reflected signals are superimposed on the original signals. Each reflection is delayed in time from the original signal, thus distorting the display. Let's try the 22 ohm resistor. Still lots of distortion. The distortion is especially great in these cases because of the large amount of time delay we get from this relatively long line. However, in cases where we are working with very short pulses, even a few feet of line used to connect two instruments together can introduce serious distortion. Only with the proper termination can we be assured that no distortion will be added. It is important to mention that it is not always necessary to have a line properly terminated. In certain applications, such as in special types of pulse generators or amplifier circuits, it is often desirable to have a line open or shorted so that a reflection may be obtained that can be put to a useful purpose. It is even possible to measure very short periods of travel time. For example, here's a scope capable of measuring extremely short intervals of time. In fact, we can measure the time required for a signal to travel down a short piece of coaxial cable and back. Since the time involved is extremely short, we will apply a very fast positive going step with a flat top. Before that step decays away, we will see a reflected signal. The end of the line, of course, is open, so that we will get a reflection. The scope display looks like this. Here is the initial positive going portion of the pulse. Here, the positive going portion of the pulse has been reflected and superimposed on the original signal, so that we get an additional upward motion of the trace. The distance between here and here represents the time required for the signal to travel to the end of the line and back. The time is precisely 1/100th of a microsecond, or in other words, 10 billionths of a second. Again, if we properly terminate the end of the line, the reflection disappears. If we short-circuit the end of the line, we get a reflection of the original step, but of opposite polarity. Again, the distance from here to here represents the total travel time down and back for the pulse. We have learned that there are many types of transmission lines for many uses, but the main use of a line is to deliver electrical energy from one point to another. The energy can be tremendously large or very minute. We have discussed how a transmission line works, that it consists of distributed inductance and capacitance, and that these combine to form what is known as the characteristic impedance of the line. We have also learned that a definite amount of time, small as it may be, is required for electrical energy to travel down a line. We have seen the effects of an open and shorted line, and we've found that in order to keep reflections minimized, we must properly match the load to the impedance of the line. Only when the line is properly terminated will there be a maximum transfer of energy with no reflections to cause distortion. Whether it be this city or whether it be this instrument, the basic application of a transmission line serves as the electrical connecting link.